Welcome to the Explainer. Okay, let's jump right into this. We've all heard the exact same analogy a million times in computer science, right? The central processing unit, the CPU, is the brain of your computer. It does the math, it runs the logic, it's the thing making everything happen. But today, we're going to peel back the layers of computer architecture to answer a much deeper, honestly way more fascinating question. If the CPU is the brain executing all these instructions, what exactly is telling the CPU what to do?
Seriously, think about it for a second. We've got registers, arithmetic logic units, data buses, memory buffers, the whole shebang. But left completely on their own, these components are really just inert pieces of silicon. They need a conductor. They need something to orchestrate the precise flow of data and sequence of events to make a program actually run. There is, quite literally, a brain inside the brain. And uncovering how it works, it's easily one of the most brilliant engineering concepts in modern tech.
To actually grasp how this conductor works, we have to totally shift our perspective. We need to zoom all the way down, way past your software applications, past your lines of Python or C++ code, and even past the basic machine instructions. We need to get down to the absolute atomic level of computing. We're stepping into the realm of what computer architects call micro-operations. When you map this out from the top down, you can really see the hierarchy. At the very top, you've got the full execution of a program. Step down a level, and we see that a program is just made up of individual instruction cycles. And, as you might remember from previous chapters, each instruction cycle is broken into smaller subcycles. Stuff like fetch, indirect, execute, and interrupt. But look at the very bottom foundation. Even those subcycles are broken down into the ultimate building blocks, those micro-operations. So, what are they exactly? Well, micro-operations are the absolute atomic, functional operations of a processor. That prefix, micro, is there for a reason. Each individual step is incredibly simple. On its own, a micro-operation accomplishes almost nothing. Think of running a program like performing a massive, complex symphony. A micro-operation is, well, it's a single, isolated note played by just one instrument. It's only when these ultra-simple operations are sequenced perfectly together that the magic of computing actually happens.
Let's make this totally concrete by looking at the standard fetch cycle. You know, the process of grabbing the next instruction from memory. It feels like one seamless action, but down at the atomic level, it actually takes 3 distinct time steps. First, we move the address from the program counter over to the memory address register. Second, we read that memory location into the memory buffer register, while at the same time incrementing our program counter for the next go-around. Finally, we move the instruction from the memory buffer register into the instruction register. Now, the true efficiency of this whole process lies in overlapping those actions. Pay close attention to that second step we just talked about. We're actually doing 2 micro-operations at the exact same time, reading the word from memory into the MBR and incrementing the PC. Because these 2 specific actions use totally different registers, they don't step on each other's toes. So our processor performs them simultaneously to save valuable time. This incredibly careful choreography happens every single time your computer fetches an instruction.
But wait, this brings us right back to our central mystery, doesn't it? Who is coordinating this choreography? Enter the ultimate conductor of our microscopic symphony, the control unit. The control unit really just has 2 basic jobs. First, sequencing, which basically means causing the processor to step through these micro-operations in the exact right order. And second, execution, actually making each individual micro-operation happen.
If you look at how everything connects, the control unit sits right where it belongs, smack in the center of everything. On the left side, you've got the inputs. This is all the information the control unit uses to understand the current state of the system. On the right side, you've got the outputs. These are the actual commands the control unit fires off to make things move. It's essentially the ultimate middle management system, taking in status reports and issuing incredibly precise directives.
Let's actually break down those inputs and outputs. To make its decisions, the control unit relies heavily on the clock to keep time. That ensures every single micro-operation syncs up flawlessly. It also looks at the instruction register to know exactly what opcode is currently executing, and it checks flags to see the status of previous calculations, like say if a previous result was 0. Based on all of this data, it outputs control signals. Some of those signals stay inside the CPU to move data between registers, while others get sent out to the system bus to talk to memory or I/O devices.
Now check out those tiny little circles labeled C1, C2, C3, and so on. These represent physical switches on the processor's data paths.
And this right here is the absolute secret to execution. When the control unit needs to move data from the program counter to the memory address register, it literally sends a control signal that temporarily opens the specific gate connecting those two components. It's like a hyperactive traffic cop opening and closing intersections at lightning speed. And the wild part? The control unit never actually sees the data being processed. It literally just controls the gates.
Okay, so we know what it does, but here is the massive, fascinating engineering challenge. How in the world do we physically build a machine capable of reading all these inputs, keeping perfect time, and firing off dozens of different control signals in exactly the right sequence millions of times a second? Well, computer architects generally rely on one of two massive implementation strategies to pull this off.
The first method is what we call a hardwired implementation. With this approach, the control unit is essentially one giant, mind-bendingly complex state machine circuit built entirely out of hardware logic gates. You take your inputs, the clock, the instruction, the flags, and you run them through a massive, tangled web of Boolean logic equations. The result that spits out the other end of those logic gates, that's your specific set of control signals.
Now, sure, hardwiring is blisteringly fast, but it presents a huge problem. In a modern processor with hundreds of complex instructions, the sheer number of Boolean equations required becomes totally unmanageable. It is incredibly difficult to design. Plus, if you make a tiny mistake in the hardware logic, you can't exactly just download a software patch to fix physical silicon. Because of this nightmare complexity, engineers came up with a brilliant, far simpler, and much more flexible alternative. It's called microprogrammed control. To give you a little context, the concept of the microprogram was actually coined way back in the early 1950s by a guy named M.V. Wilks. He proposed a super systematic approach specifically to avoid the headache of hardwired logic. What's amazing, though, is that his idea was basically dismissed as unworkable at the time. Why? Because it required incredibly fast, cheap control memory that, well, it simply didn't exist yet. But his visionary idea was quietly waiting to revolutionize how processors are built.
So what exactly is a microprogram? Well, you probably know it by its more common, everyday name, firmware. It sits perfectly in the middle ground between your physical hardware and your software. Instead of relying on physical logic gates to decide what control signals to fire, a microprogrammed control unit uses a specialized, tiny program. Each line of this program is a micro-instruction. Actually, it's a literal string of binary ones and zeros, where every single digit directly maps to whether a specific hardware control gate should be open or closed. The sheer elegance of microprogramming really clicks when you look at the microarchitecture. Right there in the center is the control memory block. Inside that memory is our firmware. When it's time to execute an instruction, the system just reads the corresponding line of ones and zeros from this memory down into the control buffer register at the bottom. Because those bits are directly hardwired to the processor's control lines, simply reading the microinstruction from memory is functionally identical to executing it. It is an absolute game changer that completely simplifies the hardware design.
And this choice, hardwired versus microprogrammed control, it literally defined the famous processor wars of the computing age. Complex instruction set computers, CISC architectures, like the classic Intel processors that fueled the PC revolution, leaned heavily on microprogrammed control to manage their massive, complex instruction sets with ease. On the flip side, reduced instruction set computers, RISC architectures, like the ARM chips inside your smartphone right now, stripped all that complexity away. They utilize hardwired control units to prioritize absolute, raw, blistering speed.
So the very next time you boot up a game, compile a script, or even just refresh your web page, take a quick second to appreciate what's actually happening under the hood. Your software relies on machine code, which relies on the CPU, which relies entirely on the control unit, the brain's brain. It's flawlessly orchestrating billions of atomic micro-operations every single second, opening and closing microscopic gates in a perfect invisible symphony. I hope this explainer sheds some light on the incredible hidden magic of computer architecture. Keep learning, keep questioning, and I'll catch you in the next one.